syllabus. Unit 1, linear differential equations of higher order with constant coefficients. Unit 2, partial differential equations. Unit 3, applications of partial differential equations. Unit 4, vector differentiation. Unit 5, vector integration. So these are the units related to DE and VC. Now unit 1 is a linear differential equations of a higher order with constant coefficients. So these are the topics related to unit 1. Now coming to definition of linear differential equation. A linear differential equation is of the form. So this is the form of linear differential equation of nth order with constant coefficients, where P1, P2, P3 and so on Pn are real constants. And the differential equation is d power n y by dx power n plus P1 into d power n minus 1 y by dx power n minus 1 plus P2 into d power n minus 2 y by dx power n minus 2 plus and so on plus Pn y equal to f of x. So it is the nth order linear differential equation. It is known as linear non-homogeneous differential equation with constant coefficients. Suppose the right hand side is 0, then it is known as a homogeneous differential equation of nth order. Now coming to notation, the operator form. So to get operator form, we have to use the operator D. So here the operator D is known as a differential operator. That is D is d by dx, d square is d square by dx square, d power n is d power n by dx power n. So that we can apply y. So we will get dy is dy by dx, d square y is d square y by dx square, and d power n y by dx power n is d power n y. Now using these operators, so substituting all these in above equation 1, then the above equation is now becomes as like this, that is a d power n plus p1 into d power n minus 1 plus p2 into d power n minus 2 plus and so on plus pn of y equal to f of x. Simply we can write it as f of d into y equal to f of x. So let it be equation 2. This is known as operator form of the given nth order differential equation, where f of d is d power n plus p1 into d power n minus 1 plus p2 into d power n minus 2 plus and so on plus pn, which is a polynomial function in D. Now the equation satisfying value, that is y is known as the solution for the given nth order differential equation. So its solution is known as a complete solution. To find the complete solution, so we will have it is the addition of two solutions, that is one is a complementary function and another one is a particular integral. Now what is complete solution of nth order with the differential equation is given by y equal to cf plus pi. So what is the cf here? Complementary function. So of the equation f of d into y equal to 0, just we have to take the right hand side as a 0 in the given equation and we have to compute its solution. The solution is nothing but a complementary function. And we have to find out pi also. So pi is given by particular integral. The particular integral is found to the equation f of d into y equal to f of x. So for total equation we have to consider particular integral. Now to find complementary function, first we have to take the auxiliary equation, and depending upon the nature of the roots we have to write the complementary function. Now what is auxiliary equation? So auxiliary equation is obtained just by replacing d equal to m in f of d into f of d and equating to 0. So what is f of d here? F of d is nothing but polynomial in D. Just we have to replace d equal to m and equating to 0. Thus we will get the auxiliary equation. So auxiliary equation is f of m equal to 0. Now depending upon the nature of the roots, we have to take the several complementary functions, real and different. If all the roots of auxiliary equation are real numbers and different numbers, then we have to define the complementary function as c1 e power m1x plus c2 e power m2x plus and so on. Suppose the two roots are real and equal and remaining roots are distinct. Then we have to define CF as C1 plus C2x whole bracket into e power m1x, because here m1 m2 are real numbers and equal, that is m1 equal to m2, and the remaining roots are distinct, that means the rest are all different, so that we have to define c3 e power m3x plus c4 m4 m4x, c4 e power m4x plus and so on. So like that, so we have to define whenever two roots are real and equal. In case 3, suppose all the three roots are real and equal and the rest are different. Then we have to define as c1 plus c2x plus c3x square whole bracket into e power either m1x or m2x or m3x, because here m1 equal to m2 equal to m3 and the rest are different, so that c4 e power m4x plus c5 e power m5x plus and so on. So it is defined whenever the three roots are real numbers and equal. Suppose four roots are real and equal, then we have to define CF as C1 plus C2x plus C3x square plus C4x cube whole bracket into e power m1x or m2x or m3x or m4x. So because m1 equal to m2 equal to m3 equal to m4 plus rest are different, so that c5 e power m5x plus c6 e power m6x plus and so on. So like that we have to define whenever four roots are real numbers and equal. Suppose the two roots are imaginary roots, that is a complex conjugate roots. So pair of conjugate roots of the form alpha plus or minus I beta, and the rest are all different real numbers, that is m3 m4 m5 and so on are real numbers but different numbers. Then we have to define the complementary function as e power alpha x into c1 cos beta x plus c2 sin beta x. So it is for imaginary roots or complex numbers of the form alpha plus or minus I beta, but the rest are different and real numbers, so that we have to define c3 e power m3x plus c4 e power m4x plus and so on. So like that we have to define whenever the two roots are imaginary and the remaining roots are real and different. Suppose two roots are imaginary and the remaining roots are real and different, and the imaginary roots are repeated twice, that is the two roots are imaginary roots which are repeated twice, two times repeated, that is alpha plus or minus I beta, alpha plus or minus I beta are the two roots of the auxiliary equation, that is f of m equal to 0, and the remaining roots are real and distinct. Then we have to define CF as e power alpha x into c1 plus c2x into cos beta x plus c3 plus c4x into sin beta x plus remaining roots are real and distinct, so that c1 to c4 already used. So we have to use the arbitrary constant from c5. So that is a c5 into e power m5x plus c6 e power m6x plus and so on. So like that we have to define whenever the two roots are imaginary roots which are repeated twice and the remaining roots are real and distinct. So like that, we have to define the complementary function for depending upon the nature of the roots of the auxiliary equation, that is f of m equal to 0. So these five cases we have to remember to write the complementary function. So once again, just we have to follow the step to find the complete solution of a homogeneous equation. So what is the meaning of homogeneous equation? So homogeneous equation means f of d into y equal to 0. Suppose f of d into y equal to f of x, then it is called as non-homogeneous differential equation. Now to find the homogeneous differential equation solution, we have to follow these steps. So what is the first step? Operator form is d power n plus p1 into d power n minus 1 plus and so on plus pn of y equal to 0. So it is the operator form of the given equation. Whenever the general form is given, just we have to write the operator form, so that we have to use the operator d. So what is d here? D stands for differential operator, that is a d equal to d by dx. So using operator D, just we have to write the given equation in operator form. That is step 1. Step 2, write the auxiliary equation corresponding to it. Just we have to write the auxiliary equation for this equation. The auxiliary equation is obtained just by replacing D equal to M. So D is replaced with M. So that we will get M power n plus P1 into M power n minus plus and so on plus Pn equal to 0. So auxiliary equation is f of m equal to 0. So that is step 2. In step 3, we have to write f of m equal to 0 and we have to solve that equation. So auxiliary equation is solved here to get the roots of the auxiliary equation. So solving here nothing but the zeros of the auxiliary equation. Zeros means roots of the auxiliary equation. So recognize the roots, nature of the roots, we have to define the complementary function in step 4. So to write the complementary function, just we have to remember these steps. Whenever all the roots are distinct and real roots, then we have to write CF as like this. That is a C1 e power m1x plus C2 e power m2x plus Cn e power mnx. Suppose two roots are equal, that is m1 equal to m2, that is m1, m2, and the remaining are rest are distinct roots, real and distinct roots. Then we have to define CF. C1 plus C2x into e power m1x plus C3 e power m3x plus and so on plus Cn e power mnx. Suppose three roots are real and equal, that is m1 equal to m2 equal to m3, and the remaining are distinct real roots. Then we have to define CF as C1 plus C2x plus C3x square into e power m1x, and the remaining are distinct roots, so that C for e power m4x plus and so on plus Cn e power mnx. Suppose two roots of the auxiliary equation are complex, that is imaginary roots of the form alpha plus or minus I beta, that is alpha plus I beta and alpha minus I beta are the two roots of the auxiliary equation. Then we have to define the complementary function as e power alpha x into cos beta x plus c2 sin beta x plus c3 e power m3x plus c4 e power m4x plus and so on. Suppose the two pair of conjugate complex roots are repeated twice, that is the roots are alpha plus or minus I beta, alpha plus or minus I beta, and the remaining roots are distinct real roots. Then we have to write the complementary function CF as e power alpha x into C1 plus C2x into cos beta x plus C3 plus C4x into sin beta x plus C5 e power m power x plus C6 e power m6x plus and so on. Suppose the two pair of conjugate complex roots are repeated thrice, then we have to define as follows. So it is the rare case. Just we have to follow these 5 steps to write the complementary function. So these totally depends upon the nature of the roots. So only these 4 steps are considered to write the solution for homogeneous differential equation of nth order. Just we have to write the operator form and we have to write the auxiliary equation. We have to compute the roots of the auxiliary equation. Depending upon the nature of the roots, we have to write the complementary function. The roots may be real and distinct, roots may be real and equal, three roots may be real and equal, imaginary roots, and imaginary roots are repeated twice and thrice. Problem for y equal to 0. So it is a homogeneous differential equation. Now we have to solve this homogeneous differential equation of fourth order. So it is of fourth order. It is given in general form. First we have to write the operator form. So using the operator notation, just we have to write the operator form. That is d stands for d by dx, and d power 4 means d power 4y by dx power 4. So replacing d power 4 minus a power 4 of y equal to 0. So it is the operator form of the given general differential equation of fourth order. Now we have to write the corresponding auxiliary equation. The auxiliary equation is obtained just by replacing d equal to m. So thus we will have m power 4 minus a power 4 equal to 0. And m power 4 minus a power 4 can be written as m square minus a square into m square plus a square equal to 0, because a square minus b square formula is a minus b into a plus b. So thus we are equating the product, we are getting four roots. So that those are m equal to plus or minus a and m equal to plus or minus ai. So here m square minus a square is equated to 0. Thus we will have m square equal to a square, m equal to plus or minus a. M square plus r plus a square is equated to 0, so that we will get m square equal to minus a square, m equal to plus or minus ai. So these are the four roots corresponding to auxiliary equation of the given fourth order differential equation. So four roots are a minus a plus ai minus ai. These are four roots. Now, depending upon the nature of the roots, the first two roots are real and the remaining rest two roots are conjugate roots of the form alpha plus or minus I beta. For real roots, we have to write the CF as C1 e power ax plus C2 e power minus ax. For first two roots, that is plus or minus a, the complementary function is defined as like this. And the rest are distinct. Here, the two roots plus or minus a, which are compared with alpha plus or minus I beta. Now, what is alpha here? 0 and beta is a. So that C3 cos ax plus C4 sin ax whole bracket into e power 0x. It is the required complete solution or general solution. So what is the general solution here? Y equal to C1 e power ax plus C2 e power minus ax for real and distinct roots plus C3 cos ax plus C4 sin ax for imaginary roots, because alpha is 0 and beta is a here. So e power alpha x means e power 0x, but e power 0x value is 1. So it is the required general solution of the given fourth order DE. 2y equal to 0. Given initial values are y of 0 is 4 and y dash of 0 equal to 1. These initial values are used for to compute the arbitrary constants C1, C2s. So it is the second order differential equation is given here in general form. Now we have to write the operator form, so that we have to use the differential operator D. So using differential operator D, so just we have to write the operator form, that is a d square plus a d minus 2 of y equal to 0. Now we have to write the auxiliary equation, which is obtained just by replacing d equal to m. So thus we will get the auxiliary equation is m square plus m minus 2 equal to 0, which is a quadratic equation in m having two roots. Now we can compute two roots by using m equal to minus b plus or minus root of b square minus 4ac by 2a. So using that formula, we can compute the two roots of the auxiliary equation. So thus we will have two roots, those are 1 and minus 2. Using these two roots, we have to write the complementary function. So here the nature of the two roots is real numbers and distinct roots. So that we have to write the complementary function as c1 e power m1x plus c2 e power m2x. That is c1 e power x plus c2 e power minus x is y value. So it is the general solution of a second order DE. But we have to find out the particular solution which satisfies these initial values also. To find the particular solution, just we have to use these initial conditions. So here y of 0 equal to 4 given. That means y value is 4 when x equal to 0. So replacing these values, we will get the equation 1 is now becomes like this. So C1, C2 are constant, which can be evaluated using initial conditions, that is y of 0 is 4 and y dash of 0 equal to 1. So using the first condition, so that x value is 0 and y value is 4 is replaced here. So we will have a equation that is C1 plus C2 equal to 4. So let it be some equation 2, and now using this equation y dash of 0 equal to 1. To get y dash means the derivative of y with respect to x. To get y dash, just we have to differentiate the equation 1 with respect to x. Y derivative is y dash. So that is y dash. C1 constant, e power x derivative as it is e power x, and plus 2 is constant, plus C2 is constant here, e power minus 2x derivative. But e power minus 2x derivative is e power minus 2x into minus 2. So that is y dash is c1 e power x minus 2 c2 e power minus 2x. Let it be equation number 3. Now substituting the initial value, that is y dash value is 1 when x equal to 0. Y dash value is 1 when x equal to 0. So replacing these values, we will have c1 minus 2c2 equal to 1. Thus from equation 2 and equation 4, we will have two arbitrary constants c1 and c2, which are to be solved these two equations to get these values, that is c1 and c2. So solving to equation 2 and equation 4, so we will get the values c1 value is 3 and c2 value is 1. Now again substituting these values is obtained in general solution. So substituting in general solution, so we will get the required particular solution. This solution, the last obtained solution, which satisfies not only the given differential equation, which satisfies the initial values also. So it is the required solution.